Hello guys, I am Fahad Iqbal. I welcome you to my channel Comparative Physics. I hope you are following my lectures. In the previous lectures, I have discussed Coulomb's law in vector forms and superposition principle. You know that electrical force exists between two charged particles. Okay, so this is one charged particle Q1 and here is another charged particle, suppose Q2. So you know that the electrical force exists between these two charged particles. A natural question arises: how is electrical force exerted when charged particles are separated? You know that these two charged particles which are separated, suppose at a distance r. Okay. So the question is, how does particle 1 know of the presence of particle 2? That is, since the particle do not touch, how can particle 2 push on particle 1? How can there be such an action at a distance? This action at a distance force can be explained by using the concepts of electric field. So today we will discuss the concept of electric field. Consider an electric charge plus Q which is located at some point O in space. Okay, if another small positive charge plus Q naught, okay, is placed at some point P, then you know that this Q naught will experience a force of repulsion. Since these two are positive charges, so what happened? It will experience a force of repulsion here in this direction. And if this is negative plus charge in place of plus charge, if this is minus Q, okay, what will happen? This plus Q naught will experience a force of attraction. Okay. So the question is, how does this plus Q or this minus Q exerts a force on plus Q naught? So the answer is, the charge plus Q or minus Q sets up an electric field in space surrounding it. That means, okay, if there is a charge, suppose here is a charge, so this charge will, what this charge will do, actually this charge will set up an electric field, okay, in the space surrounding the charge. Okay, so we define electric field as electric field due to a charge is the space around the charge in which any other charge experiences a force of attraction or repulsion. Okay, so the electric field due to a charge is the space around the charge in which any other charge experiences a force of attraction or repulsion. Remember one thing, this charge plus Q is called the source charge. This is called the source charge. Okay, because it produces the electric field, and this charge plus Q naught is called the test charge. Okay, and one more thing you have to remember, that this test charge should be as small as possible, because so that its presence does not affect the field due to the source charge. Okay, so you must be thinking of what is the strength of electric field of a charge. Okay, so the strength of electric field is described by a quantity called electric field intensity or electric field strength. So how you define it? The electric field intensity, so let me define it. The electric field intensity at a point is defined as the force experienced by unit positive test charge placed at that point. Okay, so consider a point charge plus q which is located at some point O in space, and if you bring a test charge at some point P, suppose the test charge is plus q naught, so this test charge will experience a force F. Okay, and you know that these two are like charges, so they repel each other. So here is the force in this direction. Then electric field at point P due to the charge plus q is defined as E equals to force per unit test charge. Now one more question. What is the direction of electric field? Okay, so you remember the electric field will be always in the direction of force. Okay, that is the direction of E is same as that of F. If this is the direction of force, so the direction of electric field will be also the same in this direction. Okay, the electric field is also a vector quantity. So let me write electric field intensity E is a vector quantity. Okay, so what is the SI unit of E? As we have defined the electric field intensity E as the force per unit charge, and you know that the SI unit of force is Newton and the SI unit of charge is Coulomb. So the SI unit of E is Newton per Coulomb. There is another unit of E which is written as volt per meter. Now I want to ask you, can you convert Newton per Coulomb into volt per meter? So let us see how Newton per Coulomb can be written as volt per meter. So this is Newton per Coulomb. What you have to do, you have to just multiply and divide by meter. Okay, you can multiply and divide as it will not affect the quantity Newton per Coulomb. So what this quantity is, Newton into meter, remember, just try to think what this quantity is. So this is nothing but this is the SI unit of work. Okay, so Newton meter is joule, so this will become joule per coulomb into meter. Now can you please tell me what is this quantity, joule per coulomb? Try to remember. This is nothing but electric potential, and you know that the SI unit of electric potential is volt. So joule per coulomb is volt, so this becomes volt per meter. Okay, so let us now write the dimension of E. As you know that the electric field E is defined as the force per unit test charge. So what is the dimension of F? F is the force, and you know that the dimension of force is ml t raised to the power minus 2, and in the denominator it is Q naught, which is charge, and the dimension of charge is a t, where a is the ampere and t is the time. So this will become, the dimension of E will be m l t minus 3 a minus 1. Is it clear? Well, so one thing you just need to remember, that the electric field intensity is defined more accurately as Q naught, which is our test charge, tends to 0. Okay, but what will be the minimum value of Q naught? Of course, that will be equal to the charge of electron. Okay, not less than that. So the electric field intensity, let me write that, the electric field intensity is defined more accurately as the test charge Q naught tends to 0. Let us find the electric field intensity due to a point charge. So consider a point charge plus Q placed at point O. So just suppose that here is a plus charge Q at some point O. Okay, and suppose we are to find electric field intensity, electric field intensity at a point P, which is at a distance r from O, that is OP equals to R. It means, suppose as I said, we need to find the electric field intensity due to this charge at some point P, and this point is at distance r from this. So how will you find the electric field due to this charge plus q at point P? So imagine a small positive test charge plus q naught is placed. So here we imagine a small test charge is placed. So imagine a small positive test charge plus q naught placed at P. Okay, so you know that how much force will be experienced by plus q naught. You can write the force acting on plus q naught, the force acting on the test charge plus q naught is how much? From Coulomb's law, you know that it is written as F is equal to 1 upon 4 pi epsilon naught q into q naught upon r square, and you can write the direction r cap, unit vector. Okay, well, so then you can write the electric field intensity. So the electric field intensity, then electric field intensity will be defined as, you know how to define electric field intensity? E equals to F by q naught, that is force per unit test charge. So this will become F is how much? 1 upon 4 pi epsilon naught q naught upon r square, and there is q naught also here and r cap. So this q naught and this q naught will cancel out. So what you are left with? So you are left with E equals to 1 upon 4 pi epsilon naught q upon r square and r cap. So you can write it on simplifying. So you know that 1 upon 4 pi epsilon naught is 9 into 10 to the power 9. So this will become 9 into 10 to the power 9 into q upon r square r cap. So this is the electric field intensity due to a point charge that we have written E equals to 1 upon 4 pi epsilon naught q upon r square. So what is the direction of electric field intensity here? As you know that the direction of electric field intensity is same as that of the electrical force. So this will be the direction of electric field intensity, because the direction of electric force is also the same here. Okay, well, till now we have discussed electric field intensity due to point charge. Let us now discuss the electric field due to a system of charge. Okay, so you know that in the previous case when we were discussing Coulomb's law, we have discussed the superposition principle. So the same superposition principle we will use here to find the electric field intensity due to a system of charge. Okay, suppose there are endpoint charges. So let me write here, suppose there are n point charges. Okay, let me draw the figure first and then we will discuss it. Suppose here is charge q1, here is charge q2, here is charge q3, and so on. Here suppose that charge nth charge qn charge is here. Okay, and we need to find the electric field intensity at some point P here. Okay, well, so you know that the electric field intensity due to this charge q1 at point P, the direction will be here. Let us suppose this is E1. We have imagined that a test charge q0 is placed here. Due to the charge q2, the direction of electric field will be here. Due to the third charge q3, the direction will be here. Similarly, due to the nth charge, the direction will be somewhere here is the nth charge, so this will be suppose En. Okay, and let us suppose this distance is r1p from 1 to p, this is r2p, this is r3p, similarly, and this will be rnp. Okay, well, let us write now. So suppose there are endpoint charges q1, q2, q3, and so on up to qn located in air at position r1, r2, r3, and so on up to rn respectively. Okay, well, so you know that the electric field, net electric field E at point P due to all these charges will be the sum of the electric field due to individual charges. It is E will be equal to E1 plus E2 plus E3 plus so on up to En, where E1 is net or resultant. E1 is the electric field intensity at point P due to Q1. E2 is the electric field intensity at P due to Q2. Okay, and E is the net or resultant electric field at P. So what is E1? So let us write electric field E1 at R due to Q1 is given by E1 equals to 1 upon 4 pi epsilon naught Q1 upon R1p square R1p cap, where R1p cap is unit vector in the direction from Q1 to P. So let me write this, where R1p cap is a unit vector in the direction from Q1 to P. Okay, and R1P is the distance between Q1 and P. Is it clear? Similarly, you can write the expression for E2, okay, and En and so on. Similarly, you have the expression for E2, and this will be 1 upon 4 pi epsilon naught, okay, Q2 upon R2P square R2P cap, where R2P cap is a unit vector in the direction from Q2 to P, and R2P is the distance from Q2 to P. So now, using superposition principle, you can write the net electric field at point P due to all other charges. So we can write this as E will be equal to E1 plus E2 plus and so on up to En. Okay, so what we have, E1 is 1 upon 4 pi epsilon naught Q1 upon R1P square R1P cap. Similarly, E2 will be 1 upon 4 pi epsilon naught Q2 upon R2P square R2P cap plus and so on 1 upon 4 pi epsilon naught Qn upon Rnp square Rnp cap, where Rnp cap is the distance is the unit vector from nth charge to point P, and Rnp is the distance from nth charge to point P. So something is common that we can take out, and that is 1 upon 4 pi epsilon naught. So this will be Q1 upon R1P square R cap 1P plus Q2 upon R2P square R cap 2P plus and so on Qn upon Rnp square R cap Np. This you can write in the summation form as E is equal to 1 upon 4 pi epsilon naught sum over I equals to 1 to n Qi upon R Ip square R Ip cap. So this is the electric field due to a system of charges using superposition principle. Okay, I hope you followed this lecture. If you have any doubt, please mention it in the comment box. I will try to clear your doubt there. If you have not subscribed my channel yet, please subscribe it to learn more, and like and share my videos so that more students get benefited of it. Thank you for watching.